Hey guys, I'm Autoencoders, a 2023/2024 summer intern at Pawsey, working with my supervisor Noor Haldar, and I'm here to talk about data compression. You may have used software like 7-zip or WinRAR to send your big files across the internet. They almost seem to magically shrink your files. But how do they work? In a nutshell, data compression is the method of using less bits to represent the same data. For example, let's say you had a lab report about a chemical with a really long name. Instead of writing it out every time, you could refer to it with a shorter code name instead. Just like that, you successfully reduced your word count and compressed your report. You then continue to do this with the next longest word in your report until you've compressed it as much as possible. Data compression algorithms work by finding patterns like these in a file and exploiting it to save as much space as possible. However, when the patterns are complex, basic compression algorithms can only do so much. This is especially true with large scientific datasets, petabytes in size. So to maximize our savings, what we want is a compression algorithm that learns from the data. And what better tool to use than machine learning? Using machine learning to compress files is a topic that has been steadily gaining popularity. We've seen a lot of work done in this field for images, but not much for scientific data. In our project, we investigated using autoencoder models to compress scientific data. Autoencoders are a simple framework consisting of an encoder and a decoder. The encoder passes our data through multiple layers, reducing in size, producing a compressed vector representation of our file. This smaller file can easily be sent over. But to retrieve the original data, we need to pass it through the decoder, which is basically a reverse of the encoder. The key thing to note is that we aren't reproducing our original data. We're just trying to recreate it as closely as possible with our machine learning model. This means our compression algorithm is lossy, as we lose some details of our original data. While in many cases, this is the opposite of what we want. But when you have petabytes of data, you're looking for general trends in the data rather than looking at every single data point. But as this is science, we do need some guarantees on how much our data varies. This is why we implemented a method of bounding the error of the model. If the reconstruction error is greater than a certain percent, then we'll just save the original value. The more accurate we want the data to be, the less compression savings we get. So just by training our model on a small subsection of the original data, we get a highly specialized algorithm perfect for compressing very large files. In our experiments, we've shown our model capable of reducing file sizes to 1/250th of the original size, the next best algorithm only reaching 1/100th of the size. There is a lot of potential with this new direction for data compression. However, there are a few caveats. When sending the data, a copy of the model must be sent as well to be able to decode the data, which adds overhead to the file. This means it's only suitable for very large or continuous file transfers. Further research also needs to be performed to see whether the structure of the data has been altered as a result of this compression. Depending on the use case, patterns in the noise of the data could be very important. So while this tech may not be useful for the everyday researcher, it may just prove vital for large scientific surveys. Once again, I'd like to thank my supervisor Noor and the wonderful staff at Pawsey for giving me this lovely opportunity. Thank you.